Okay. What just happened here? Who knows? So here's the things we have coming up in the next few days. Exam 1, not exam 1, exam 2, is in class on Wednesday. And the topics for that are everything up through Newton's laws. So no circular motion and nothing new that we talk about today. Anybody have any questions about the test? Yeah.
Does it include like the other tests we took?
Yes, it's cumulative. So yes, you should review all the way back. Just be sure that you still remember how to answer questions like that. Any other questions? Okay, and then next week is lab exam 2. And the topics for this are all the things that we've done in labs up through the review we did last week. We're doing a new one today, this week, but that's not going to be on the test. And I did finally finish grading lab exam 1, so I'll give those back to you in lab this week, and we'll go over some of the questions that people had trouble with semi-regularly. So yeah, I'll just I didn't bring those here, but I'll give those to you next in your lab. Any questions about the lab exam? Okay. Well, let's start by doing some just questions related to the test. I'll give you time to work on stuff just to get it sort of back in, get used to doing that stuff again. And then I think we're going to go into new material, but we'll see where we get with this. So first, let's say you have an elevator with a 5 kilogram mass hanging from the ceiling and a 10 kilogram mass hanging from that. And let's say that the elevator is accelerating up at 3 meters per second squared. Calculate the force vector applied to the 5 kilogram mass by the bottom cable. So, okay, but just take a few minutes, start with a free body diagram. You always need a free body diagram if you're going to use Newton's second law, and see if you can work through this. So a problem like this, so what's the category of problem that this is? This is the one where it's that, and it's also one where you have two things with related accelerations but not the same acceleration. And so the way we're going to do it is, because it's rolling and sliding, when we deal with this one, we're going to use that rotated coordinate system like this. When we're dealing with hanging mass, we're going to use a regular coordinate system. And you have to start by choosing one of these bodies to look at first. It doesn't matter which one you choose. I'm going to start, I just tend to always do the one that's farthest on the left, I think. So I'm going to start with the hanging mass. Okay, so free body diagram. You have 1 times 9.81 for the weight, and a cable force T, and nothing else makes contact with the boundary. Newton's second law says 0, negative 9.81 plus 0t is equal to the mass, 1 kilogram, times the acceleration. And on the first body, remember, you're always just using a positive variable a along whatever axis the thing is moving. Is this hanging mass moving along X or Y? Y, so I'm just going to write this as 0a. And sometimes you can tell which way it's going to accelerate, and this one you can't really, but it doesn't matter, because whether you can tell or not, you're always just going to put in a. Okay?
What about for the other body? Positive.
So for the other body, we'll get to that. And that's sort of, I think that's the trickiest thing about this kind of problem. So the y equation says negative 9.81 plus t is equal to a. We can't solve that because there's two variables in it, but we'll set it aside for later. And now I'll go to the free body diagram of the rolling cart. There's a weight force down of 5 times 9.81. There's a pushing force that's perpendicular to the surface. And there's a pulling force from the cable with the same magnitude as in the first body. And one thing we're going to have to do here, since we have this rotated coordinate system, we're going to have to figure out the components for the weight force. So it has a magnitude of 49.05. And this angle between, so the negative y-axis is the 270-degree line. Since the ramp is 10 degrees from the horizontal, this weight force is going to be 10 degrees from that 270 line. And now you can use that to think, are we going to add or subtract 10 degrees from 270 to, yeah, in this case it's add, because remember you start at the positive x-axis, go counterclockwise, so you get to the 270, and then you have to keep going 10 more degrees to get to the vector. And so this is going to be 49.05 times the cosine of 280 degrees, and 49.05 times the sine of 280. And I got 8.52, negative 48.30. So what that is the weight force in this rotated coordinate system. And so now we can go to Newton's second law. The cable force is in the negative x direction, so negative T0. The normal force is in the positive y direction, so 0n. The weight force we just calculated is 8.52, negative 48.30. That's the 49.05 in the free body diagram. And then that's equal to the mass times the acceleration. And here's where we have to think about the plus minus sign of the acceleration for the only time really in any kind of problem. So the way to do that, go back to the first body and imagine that the first body moves in its positive direction. So what we're imagining is the 1 kilogram mass moving an inch up. Where would the 5 kilogram mass move? Yeah, it would move down and to the right, which is its positive x direction. And since a positive motion of the 1 corresponds to a positive of the 5, we're just going to write this as A0.
So why is T negative?
T, so we figured out from the rules of pulling that, it's always parallel to the cable away from the body. So we know it's that way. And then you're just looking at the coordinate system. Like, what direction is this in the coordinate system? It's in the negative x, so that's why. Any other questions right now?
I had a question.
Yeah.
Why is the 10 degrees on the slanted direction?
Yeah. Well, it has to do with which way the coordinate system is rotated, because that weight force is always just straight down, And so since the coordinate system, imagine like if you had the normal coordinate system, that weight force would just be in the negative y direction, right?
Yeah.
And now as you tilt it, that negative y is moving to the left.
Yeah.
You see that? And that's why.
Okay.
That's why it works that way. Okay, so we got this. We have to think about which of these equations is useful. We're looking for, from our first equation, our variables are t and a. So we want to find the one of these equations that have those two in it. So it's the x equation that we want. So negative t plus 8.52 is equal to 5a. That's our second equation. And now we have our system of equations. So negative 9.81 plus t is equal to a. And our second one says negative t plus 8.52 is equal to 5a. You can always solve that by substitution. In this case, you can add. It's a little quicker to just add the two equations. If that doesn't make sense to you, if you don't remember doing that stuff, forget about it. But so if we add, negative 9.81 plus 8.52, you get negative 1.29. The t's cancel each other. That's why I'm doing it this way. So we don't have any t's, and then this is 6a.
Negative 2.15. All right, 0.215.
0.215, yeah. So A is negative 0.215 meters per second squared. The hanging mass had this acceleration. So now we just plug in that A value. And so the acceleration vector of the 1 kilogram is negative 0.215 meters per second squared. Or in other words, it's downwards at 0.215. Anybody have any other questions about that one? Okay, so this time let's say that we have a 100 kilogram object pulling on a 200 kilogram object. There's a force this way of 1,000 newtons. The coefficient of friction for that 200 kilogram box is 0.1. And we want to calculate the acceleration vector of the 200. And second, we want to calculate the force the cable applies to the 200. Okay, so see if you can think your way through that one. So that would look like this. So there are the two bodies. There's the 1,000 Newton force here. There is $981 for the weight there, and $1962 for the weight there. On the rolling cart, there's a pushing force. I'll call that N100. On the sliding body, there's a pushing force N200. This was 1,000. And then there's one more force in here. There's a friction force that's going the opposite the direction of motion, so this way. And that's equal to the coefficient times the pushing force on this body. So times N200. Well, let's write out the equations and see what we have. So the x equations say negative 0.1 N200 plus, I don't know why I wrote it like that to start with. Let's write out the vector equation first and then go to those. So we got the friction, negative 0.1 N200, 0. The weight force, 0, negative 1962. The pushing force, 0, and 200. The weight force of the smaller one, 0, negative 981. The pushing force on the smaller one, 0 and 100. And the 1,000. One, two, three, four, five, six. 1, 2, 3, 4, 5, 6. And then that's equal to the mass of the whole system, which is 2943. No, just the mass. That is 300. Times the acceleration that's happening along the x-axis, so that. All right, so we have these two equations. The x equation says negative 0.1 n 200 plus 1,000 is equal to 300a. The y equation says negative 1962 plus n 200 minus 981 plus n 100 is equal to 0. Okay, normally, and on any problems I would give you on a test, you can use the y equation to calculate n and then plug that into the x equation. In this case, though, we can't do that because you have two variables in your y equation. Okay? So now at this point, I'm going to isolate something else, and we're just going to look for equations that are going to let us plug things in to solve these. So the next thing I'm going to do, since we want to be able to calculate, in order to figure out this friction force, we need to calculate N200. I'm going to isolate the sliding mass. Okay, so I'm going to just set these aside. We'll come back to them. And I'll draw a free body diagram of the 200. So you have a weight force of 1962. The pushing force, N200. The pulling force from the other thing, so that's this way and has a value T. And then the last one is the friction force that's opposite the direction of motion, and it's equal to 0.1 times that N200. Okay, and let's see what we have from Newton's second law for this. So we get negative 0.1 N200, 0 for y, plus the weight, 0, negative 1962, plus 0 N200, plus T0. So that's all four of those forces. And that's equal to the mass of this system times the acceleration, A0. And this one, we can't solve the x equation. That says negative 0.1 N200 plus T is equal to 200A. But the y equation does give us something we can solve. Negative 1962 plus N200 is equal to 0. Okay, so I'm going to do this one first. Let me number these. So here's our equation 1, 2, 3, 4. I'm going to first use equation 4 to find N200. So add 1962 to both sides and you get that N200 is equal to 1962. And then plug that into equation 1. So we have negative 0.1 times 1962 plus 1,000 is equal to 300A. So negative 196.2 plus 1,000 is equal to 300A. And so A is equal to, that's 803.8 divided by 300. So you get that the acceleration, the acceleration is 2.68 meters per second squared. So all that was our usual first step in a problem like this, but the friction made it more complicated. But now we have an expression for the acceleration. It's always been this, we just didn't know what A was before. So the acceleration vector is 2.680. Or in other words, it's accelerating this way with a magnitude of 2.68 meters per second squared.
We don't have to plug that into the 200. We'll find acceleration at the 200.
No, you don't, because the acceleration of everything in problems like this is the same. Yeah, that's right. So you can plug it into whatever, and it'll all give you the same answer. I would have done it here. I would have plugged it into equation 3, but notice we also have this t in here, so we couldn't have solved it yet. So I just plugged it into the one that, you know, we could solve. But now that we have that, we're trying to figure out the force the cable applies to the 200. And so now we can use this A value in equation 3 to find that T. And so that says negative 0.1 times the N200 that we calculated, 1962, plus T is equal to 200 times 2.68. And so T is equal to 732.07 newtons. Okay, so what we're trying to find is the force on the 200 by the cable. That's always been this. We just didn't know what T was yet. And so the force on the 200 by the cable is 732.07 for X, 0 for Y, or a force going this way with a magnitude of 732.07 newtons. So if you try to do this with a cable that can only support a force of 500 newtons, it wouldn't work. It would break. Okay, I got to be honest with you. When I wrote this out, I did not realize that the friction was going to cause that much of a problem. So I didn't mean to give you a problem this far outside our usual thing. But you won't have to do anything like that on a test. But you always can. I mean, the one sort of thing that you see here is like you always can just keep trying new things, figure out what you can solve. Every equation that you come up with, as long as you don't make any mistakes, you can go back to later and plug stuff in, So, okay, let's do another one, and let's do a more straightforward one. So let's say this one's 30 kilograms, this one's 15 kilograms, and they're connected by a cable. And you have a force on the 15 kilogram thing of 100 newtons, and a force on the 30 of 250 newtons. So calculate the acceleration vector. And then second, calculate the tension in the cable. Okay, take a few minutes and see if you can work through that.